Okay, so this is the June 14 paper, the Chem 2 paper, so the most recent one, besides obviously the June 15 paper that's going to be tomorrow. The aim of this isn't to cover topics in detail. It's just to kind of go through the paper, maybe some tips and sort of go through, and generally kind of get through the paper. It's an hour and 45 minutes, the paper. My aim here is to probably do this in about an hour and 4 minutes. I'm hoping for 100 marks, 105 minutes. So just over a minute per mark. Obviously, you can save as much time on the sort of more simple questions as you can. Mechanisms, halogens, all that sort of stuff covered in this topic. Shouldn't be particularly any calculations in this though. Right, let's have a look. So, first question: a dynamic equilibrium is established when gas A is mixed with gas B at a given temperature. And we've got a reaction here: A plus B. And I think what we're supposed to have here, although it's copied weirdly, is that. Oh, Java update. So we've got an equilibrium there, and obviously dynamic equilibrium given. So for some reason the symbol hasn't gone across. There we go. Figure 1 shows that the concentrations of reactants and products change with time. So the concentrations here, so as time goes on, A and B decrease and reach a plateau, C and D increase and then plateau, plateauing at the same point around about this sort of kind of level here. If that was a straighter line, that would be perfect. In fact, I think I can do a straight line. Somewhere around there. Brilliant. Okay, on the appropriate axis of figure 1, place an X to show the time when equilibrium is first established. Oh, well, that worked out quite well actually. I did that before the question. So there's my line. So that's my first point there, 1A1, and it's the point where these lines are becoming horizontal. So just about there, I think. I mean, look at that top line. That's pretty perfect. Maybe slightly across might be a good one, but there is no definitive point here. It's sort of where the lines are becoming horizontal, because that's the point where equilibrium is becoming established, and that leads us into this next one. So state how the rate of the forward reaction and the rate of the reverse reaction are related to each other at equilibrium. Well, those rates are equal. Normally, you would be expected in a question like this, it'd say describe what happens at equilibrium, and it would be the rates are equal here. We just have to say here, and I'll explain that terribly, there's no requirement here to talk about the rate, whereas normally in this kind of question there is, because they're telling us what can you say about the rate. We just have to say they are equal. I've put rates there rather than they, but that's fine. 1A3, give the meaning of the term dynamic in the context of a dynamic equilibrium. So it's the idea here that it's not a fixed equilibrium. We aren't reaching a point and then stopping. We have forward and backward reactions occurring at the same time. So this real point that it's dynamic, it's moving, there are reactions occurring, but because the rate is equal, there's no sort of overall change. 1C1, the total pressure in the system is increased at constant temperature. State and explain the effect, if any, on this change in the position of equilibrium. So there's my thingy here. Right, very clever question, this one. 2 moles here, 2 moles here. If I increase the pressure, it was pressure, wasn't it? Yeah. There are no more moles on the left or right hand side. Therefore, the pressure is not going to affect this. Okay, so we're going to get no effect, no change. Okay, do be aware that's not always going to be an increase or a decrease. And the reason being equal moles on both sides. So nice easy sort of couple of marks there again. So no change, equal moles on both sides. So when it increases, it can't move. When the pressure increases, it can't move to a lower mole side in order to decrease the pressure. It's not going to happen, so there'll be no change. 1C2, state and explain the effect, if any, of this change and the time taken to reach this equilibrium. Right, so this one is basically, we're looking at the fact that it's looking at the time taken. It's kind of a rates question. So the effect is increase in pressure. This will decrease the time taken. The reason being that it's the equivalent of increasing the concentration of these gases. So you're increasing the pressure, you're forcing them closer together. So more particles, and this is directly GCSE really, increasing the concentration, rates of reaction, more particles in given volume, and I would say they're more frequent collisions and more successful collisions in a given time. So the idea here that there's more particles in the given volume, not just more particles in that specific volume, the concentration is increased, the frequency of the collisions is increased, and that leads us to more frequent successful collisions as well. We've got 8 marks there, so equilibria, question 1. Let's go on, question 2, a bit of kinetics. So here's a Maxwell-Boltzmann distribution of molecular energies in a sample of gas at temperature T, and then we've got my thingy here. Okay, one of the axes is label the other axes. Nice one here. So I would say number of molecules, range of answers here, amount, all the rest. I would go number of molecules being this axis there. State why the curve starts at the origin. Right. The reason being here, and they've given you the 0 points there to kind of help you. The reason it starts at the origin is that no molecules or particles, I'll call it molecules, so none have 0 energy. They will all have some sort of energy, so none have 0 energy. That's very important there. None have 0 energy. Which of the following, A, B or C, describes what the value of Y represents in figure 2? So this is Y, top of that peak there. A, the energy needed for a successful collision, well, that's our activation energy. The minimum energy needed for a reaction to occur, that's also our activation energy. C, the most probable energy, so we're going to have C right there. Boom, one more nice little mark. 2D. On figure 2, draw a distribution of molecular energies in the sample gas at a higher temperature. So higher temperature is going to, it's going to mean that more, so if we imagine this is where activation energy is for the sake of sort of, I'll tell you what, let's have that as a nice line again. So this is our activation energy here. So what we want is we want more molecules to really to fit into this bit here. We're not changing the number of molecules, and that's the area under this. So what we're going to do is we're going to shift it to the right. It needs to remain something similar though. So it's going to come up, it's going to go out like this, and then it's going to look something like that. So it's a little bit less high, but we'll note now that the number of molecules, the most probable one here, my dashed line there, is now at a higher energy. So more probable, the higher number of molecules, if you like, the most probable energy is higher than it was before. So over here, shifted to the right. The whole curve's been shifted to the right, and now, if this is my activation energy, still the same, we now have a large number of molecules there. So that's what the curve wants to look like. 2 east, the pressure of the original sample of gas is doubled at temperature T. State the effective energy on this change on the value of Y, the pressure of the original sample. Pressure is not going to change it, so no effect there, no effect at all. It's not going to change distribution. Question 3. Antimony is a solid element that is used in industry. The method used for extraction of antimony depends on the grade of the ore. Antimony can be extracted by reacting scrap iron with low-grade ores that contain antimony sulfide, Sb2S3. Write an equation for the reaction of iron with antimony sulfide to form antimony and iron 2 sulfide. So, let's have a look at this. So, iron with antimony sulfide. So there's my iron, there's my antimony sulfide. We know that we're going to produce antimony on its own, and we're going to produce iron sulfide, so it's going to be FeS And we need to balance this now. So Sb, let's put a 2 there to start with. Let's put a 3 there. A 3 there. Are we right? That looks okay to me. Yep. Again, multiples are okay, but in this one you shouldn't really need multiples. But if you want to double them up, then fine. It's not the end of the world. So what happens to iron in this reaction? Well, the iron is obviously starting as iron, and it's becoming iron 2 sulfide. So it's becoming Fe2 plus. Balancing this up, 2 electrons. So the iron is losing 2 electrons, but via convention, we'll stick it on the right hand side there as plus 2 electrons. First stage, the extraction of antimony from a higher grade ore. Antimony sulfide is roasted in air to convert it to antimony 3 oxide, Sb2O3, and sulfur dioxide. So antimony sulfide, again, what was that? Sb2S3. We're going to react it with oxygen, roasting in air. We're going to produce Sb2O3 and sulfur dioxide. So let's balance up this straight away. 3 there. Balances my sulfurs. 6 oxygens, 9 there. 2 antimony, so my oxygens need balancing, so I've got 9 on this side. 6, add 3. This needs to be 4.5. And that's all balanced up. Nice. Identify one substance that is manufactured directly from the sulfur dioxide formed in this reaction. I would probably go sulfuric acid on that one. Sulfur dioxide making sulfuric acid. Yes, happy with that. Other options as well, sulfur trioxide and things. I would go sulfuric acid personally. Contact process. 3C in the second stage. Oh, there are calculations, of course, yeah, but there's obviously the energetic stuff, enthalpies. In the second stage, the extraction of antimony from a higher grade ore, antimony 3 oxide is reacted with carbon monoxide at high temperature. Use the standard enthalpies of formation table 1 in the equation given below table 1 to calculate a value for the standard enthalpy change for this reaction. So, we're dealing with enthalpies of, I'm not going to rewrite the equation though, I'm going to leave the equations there. We're dealing with enthalpies of formation, so we're forming this, we're not going to worry about forming this because we've already given it there. Actually no, hold on, we'll look at that in a second, and we're forming this. So, arrows. We are going to have our arrows going up like this. I'm going to do it in a cycle way because personally I love a good cycle. You could do formation, formation is a PR job, so products minus reactants. Don't really like doing it that way. I find it very, very clunky. I've got no time for it. Well, it's not really clunky, I guess. I just don't like it. I prefer the cycle way, so I'm going to leave it like this. Just bear with me while I work out what I'm doing here. So this is my little box at the bottom. Okay, if you really don't get this, I'm not going to explain it now. Look back at one of the other videos, it's an energetics one, I think it's part 3. Talks about the Hesse cycle and things. Don't worry about it right now. But this is my box at the bottom. What it's basically telling me is that these are my elements in their standard states, and I'm using these to form this stuff here. So these arrows are arrows for the reaction. So for example, this one here would be Sb. It's going to be 2Sb add O2, give me this Sb2O3, so 1.5, etc. So that's what these arrows are actually showing. They're the reaction arrows. Now in terms of how this works, add all the various bits on here. So we've got to take into account multiples here as well. The definition for the enthalpy of formation is the enthalpy change when 1 mole of substance is formed from its constituent elements in their standard states and all the rest of it. So because I'm forming 3 moles here, this for example is going to be 3 times minus 111. This is just going to be minus 705. Sb is going to be 2 times 20, and CO2 is going to be 3 times minus 394. This one here, you might say, well, what's going on here? This doesn't make any sense because it's we're forming the element, but note that it's not in its standard state. This would be SB solid, SB liquid, so it's changing state there. Okay, so we're not forming just the same element, we are changing. It's being formed from its elements in its constituent states, but it is not in its constituent state as a liquid there. So that's, just bear that in mind. I think our numbers there are okay. Yeah, so what I would do now is I would say, well, this is my start, this is my finish over here. So finish, start, and I would go against the arrows like so. And so I'd stick my values in. I would say 705, add 3 times 111, add 2 times 20, add 3 times minus 394, and we should find that that comes out at minus 104 kilojoules per mole. That's our calculation. As I said, you can do products minus reactants, and it's a lot quicker that way. I prefer the cycle. It's just what I prefer to do. It's completely my choice there. But the products minus reactants, you would just do literally products minus reactants there in the value. So it's a lot quicker. But I don't like it for the sake of the understanding that's going on. But it's completely your choice. 3C2 suggests why the value for the standard enthalpy formation of liquid antimony given in table 1 is not 0. Okay, so I would say liquid antimony is not its standard state. And actually that's something that we mentioned, the idea there of it being the liquid is not its standard state, therefore boom, 1 mark. Say the type of reaction that antimony 3 oxide has undergone in this reaction. So that's our oxide there. It's going to just antimony on its own without even looking at oxidation numbers. The oxygen has been removed by the carbon monoxide, therefore it's been reduced. Deduce, oh, I hate these deduce. Deduce one reason why the method of extraction of antimony from low-grade ore described in part 3A is a low-cost product. Do not include the cost of the ore. I would go instantly. Oh, hold on, 3A, not there. Okay, it's there. Look at that. It's scrap iron. Got to go back a little bit there, haven't you? Iron used is scrap. So obviously it's scrap iron. It's going to go to waste. It's cheap. Boom. 10 marks. Energetic stuff. Let's crack on. Question 4. Group 2. There are many uses of group 2 metals and their compounds. State a medical use for barium sulfate. Love this. Good old barium meal. Standard question is, why is this safe? So barium ions are toxic, they're poisonous, but barium sulfate is insoluble. Okay, so BaSO4 is insoluble. Be specific here. Barium sulfate is insoluble. Don't just say it is insoluble, because then what's it talking about? It's the idea of barium sulfate being insoluble. So do be specific. You could get tripped out there. Magnesium hydroxide is used in antacid preparations to neutralize excess stomach acid. Write an equation for the reaction of magnesium hydroxide with hydrochloric acid. Magnesium hydroxide, hydrochloric acid. Oh, terrible thing. Magnesium chloride and water. Standard neutralization, acid-base reaction. Bam, bam. Job's a good one. Absolutely nailed that one. 1 mark there. See, they're not. I mean, at this level now, AS, you expect to just be able to do these equations, MgCl2, not MgCl, and all the rest of it. Okay, if you don't understand it, there are ways to work it out. I'm not going to explain it now, but you know, just got to sort of get your head around it. You will lose a few marks, certainly in AS, if you can't do your balancing equations and writing simple equations. Solutions of barium hydroxide are used in the titration of weak acids. State why magnesium hydroxide solution could not be used for this purpose. I would go with magnesium hydroxide is only sparingly soluble. So it's only sparingly soluble, not very soluble, which means it's not going to be very good really when we're sort of titrating it, because we're not going to know the proportion of hydroxide ions that are actually within solution. We need to have that complete solubility to enable to actually carry out the volumetric analysis that titration allows. Magnesium metal is used to make titanium from titanium 4 chloride. That's come from nowhere. Where is that? I suppose it's group 2, but it's a bit out there. Anyway, magnesium with titanium 4 chloride. So magnesium with titanium 4 chloride. It's going to be TiCl4. This is one of those that you are expected to know because it comes up in the titanium extraction. There we go, 4, yeah, done. One more mark there. Again, you can work out most of it, but it's just a displacement reaction in order to produce the pure titanium there. Sodium can also be used in that process. Magnesium burns with the bright white light and is used in flares and fireworks. Useful. Use your knowledge of the reaction of group 2 metal with water to explain why water should not be used to put out a fire in which magnesium metal is burning. So, I think it's probably at this point worth thinking, well, what happens? So magnesium in this reaction, magnesium add water. What do we get? Well, we produce magnesium hydroxide. Not particularly a worry. But we also produce, just make sure this is balanced. 4, yeah. We also produce hydrogen. This guy is not good. It's a fire. So we've got a fire, we're adding water. Whilst we might put out some of the flame, the reaction that takes place, they have that cooling effect of the water, the reaction that could take place is going to produce hydrogen. This is explosive. And that's bad. Okay, that's really, really bad. So the first mark here is the idea that hydrogen is produced. I've used it in an equation there and I've circled it because I just quite like the look of that. If you could just say, because hydrogen is produced, you do not need the equation. It just makes more sense to me to kind of work it through in a more logical sense. And it's explosive. Bam, another 2 marks. So we're in question 4 now. We're 24 minutes in. Another 7 marks there. Let's hit question 5. I'm waiting for some mechanisms to come up. And here we go. First mechanism there. Obviously, a little bit different, no arrows involved, but we've got some free radical substitution. We've got the reaction of trifluoromethylamine being formed when trifluoromethane reacts with chlorine. Initiation step. What's brilliant about this is the initiation step is always the same. So the chlorine there, homolytic fission being broken down into the radicals there. Boom, 4 marks for this first propagation. Well, our chlorine radical comes along and it reacts with that initial substance here. It reacts with the trifluoromethane. Okay, that's our first bit. Okay, let's get this tidied up. And as in the video that I've done previously, that removes a hydrogen. Oh, dear me. Let's get rid of that. It looks awful. Removes a hydrogen, this case there, boom, CF3. I am going to go that being there, because I personally think that's where it should be, which I'm fine with. They will accept it being on this side. I would stick it there. I think it's just good practice. Hydrogen chloride is also given off here, obviously because the chlorine radical and the hydrogen. We've now got this funny trifluoromethane radical thing, which is going to go on. Obviously that's got to do our next bit of reacting. That now reacts with the chlorine, and it's the same concept no matter what you do each time here. Produces our final product and another chlorine radical, which obviously is sort of like this chain reaction, just goes along now. Termination step to form hexafluoroethane. So please bear that in mind. Hexafluoroethane, we're looking for this guy here, where each one of these is fluorines. So it's got to be these two. So it's got to be 2. And we'll call it, we'll go C2F6 on that. So 4 marks there. Initiation step. First propagation. Chlorine radical gets involved, takes a hydrogen, forms a funny other radical, hydrogen and chloride. The radical that was formed now reacts with the chlorine to produce our final product, and another chlorine radical which goes back and reacts, yada 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 yada, bam, termination. This step to produce hexafluoroethane. Give one essential condition for this reaction. UV light. You could say high temperatures and all the rest. I think you're just sort of messing around there. I'd just go UV light. It's a lot easier. High temperature is fine. Specified temperatures, just put UV light though. It's a lot easier. In some refrigeration systems, CHF3 has replaced CClF3 because of concerns about ozone depletion. Identify the species formed from CClF3 that is responsible for the catalytic decomposition of ozone in the upper atmosphere. Lots of words right there. Right, so what is formed? It's the chlorine radical, that sneaky little chlorine radical that causes the ozone to be decomposed. Finally here, write an overall equation to represent the decomposition of ozone into oxygen. All we need is this overall one, so it's O3 going into O2, and then it's a case of balancing that up. Bam, like that. There's your 7 marks. Question 5, we're done with that now. We're on to question 6. Oh, 2 spare pages. Wasting, trees are dying everywhere. This question is about group 7 chemistry, so we're on to halogens now. So seawater is a major source of iodine. The iodine extracted from seawater is impure. It's purified in a 2-stage process. Stage 1, stage 2. Okay, state the initial oxidation state. Good, so we're getting some redox in now. State the initial oxidation state and the final oxidation state of sulfur in stage 1. So the oxidation state of sulfur in SO2. Straight away, we're going bam, I'm going +4 because the oxygen is -2. So we've got, to balance up to give us 0, it must be that. S here I know is +6 because I know that's what it is in sulfuric acid, but if you're unsure as to how, each oxygen is -2, so that's -2 times 4. Each hydrogen is +1. The sulfur therefore must be +6, so the whole thing balances to give 0 as its overall state. State in terms of electrons, what's happened to chlorine in stage 2? So chlorine has gone, I'm going to draw it out. I think it's always useful here. So chlorine has gone like this, hasn't it? Oh, what are we going to say here? Gained 2 electrons. Yeah. So it's gained. Boom. They're not allowing reduction in this case because they do want you to specify in terms of electrons what is actually happening. So the idea of it's gaining electrons, therefore reduction, but it is gaining electrons. Okay, good. Balance the equations for the reaction that forms sulfur. So we're balancing this top one here. Right, let's have a look. So where are we going to start on this? I hate these equations. So we could go initially balance the iodines. We could go 2 there. That balances our iodines up. We needn't use numbers in every space, although they perhaps do want numbers in every space. We'll see. So balancing our iodines up. 2Ks, need to balance that with the 2 as well. This probably isn't right, but we'll see where we get. 2 H's, 4, so we need a 2 there. That's 2 SO4s, 2 SO4s. Where are we at there? 2 S's, 2 S's. 3 there. That's not going to work, is it? Eight, 9, 8, yeah, so we're going to have to change this. Alright, scrap that. Let's go higher, let's go multiples. 2, 4, 4, 4, 4, 6, 3, that's not going to work. 3, 6, 6. 6 SO4, 6 8, 24, 7, 28, 4. Yeah, Not a very easy one to balance that. Horrible equation. Ugh. I'm going to leave that rapidly. Awful. I think some of these, I mean, I find them quite hard to balance some of these. You've just got to sort of pick some numbers and see where you go with them. Difficult thing is here that you've got the SO4 and the S, which sort of throws it slightly. Anyway, done that. Deduce the half equation for the formation of iodine from iodide. Straight away I know we're going to have something like this. There. I minus iodine. Bam. Deduce the half equation for the formation of hydrogen sulfide from concentrated sulfuric acid. So we're forming hydrogen sulfide from sulfuric acid. Right. Where are we at? Okay, let's balance the oxygens first. So I'll just stick them here. 4 H2Os. We've got 8, 9, 10. So we're going to need 8 H plus to balance it up and 8 electrons to balance the charges. Boom, there we go, 1 more mark. 8 H plus, 8 electrons, yeah, H2S. And 4 H2O, yeah, fine. 6C, yellow precipitate is formed when silver nitrate, oh, nice and comfortable now. Silver nitrate solution acidified with done. Right, the simplest ionic equation formation of the yellow precipitate. Right, we're on 6C. So it's the silver ions that are doing the business there. It's the iodide ions in the whatever it is, potassium iodide, whatever it is, and we're producing silver iodide, and that's the lot. Boom, 1 mark there. State what is observed when concentrated ammonia solution is added to this yellow precipitate. So iodide does not dissolve, so no change. No visible change, no precipitate does not dissolve, whatever. Iodide, if you remember, is the one that doesn't dissolve in any. The chloride dissolves in dilute, the bromide dissolves in concentrated, the iodide doesn't dissolve at all in ammonia, so that's another mark there. Why is it acidified? To remove ions that would I like give a false positive, i.e. that the ions there produce a precipitate that appears as though it is giving you, say, the result for chloride or iodide or bromide, whereas actually it's not, it's something else reacting, so it's a false positive, or that would interfere, or you could be more specific, you could say remove carbonate hydroxide ions. You don't need to really specifically know that. It's the idea of removal of ions, though, to stop interference or stop false positives. That's the key thing. Explain why dilute hydrochloric acid is not used to acidify. Pretty clear that hydrochloric acid contains chloride ions. Well, that doesn't answer the question though. So would produce a white precipitate, which obviously is fairly useless. We don't want that. We want just the iodide ions to be showing up, which would give us the yellow. We do not want white. Oh, still going. Chlorine is toxic to humans. Toxicity does not prevent the large-scale use of chlorine in water treatment. We give one reason why water is treated. I'd say to kill microbes or bacteria. Right. I thought it was going to go here. Explain why the toxicity of chlorine does not prevent this use. Benefit outweighs the risk. Standard statement there to make. Benefit outweighs the risk. The health benefit outweighs the risk of the toxicity. Write an equation for the reaction of chlorine with cold water. Just one that you're expected to know. H2O forming this HClO and HCl. It's the one I would go with. Are we balanced up? Yes, we are. Give the formulas of 2 different chlorine-containing compounds that are formed when chlorine reacts with cold, dilute aqueous sodium hydroxide. NaCl, NaClO. So they're the 2 things that are produced in this reaction with the cold, dilute aqueous sodium hydroxide. Those you're expected to know. Okay, write the equation out if you must, but those are just the two things. And remember, it's that disproportionation reaction there where we have the different results, different chlorine species formed. So another 14 marks there. Question 6. I am going through this at a reasonable pace. I don't want to mess around with 37 minutes in. Making good time at the minute. Finally, a bit of organic. Love me some organic. Table 2 gives the names and structures of some structural isomers with the molecular formula C5H10, isomer 1 pentuene, cyclopentane, isomer 2, 3-methylbutyne, 2-methylbutyne, 2-methylbutyne. There's the structures for each one. So what's meant by term stereoisomers? Standard definition. Same structural formula. Okay, you can't have molecular, which I think is just annoying, but there we go. Same structural formula, different spatial arrangement of atoms. I'd probably go atoms slash groups. Same structural formula, 1 mark, different spatial arrangement, or the atoms or things are arranged differently in space. It's the idea of them being different in space. That is an A there, and that's a T, spatial. Draw the structure of the E stereoisomer of isomer 1. So it's pentuene we're dealing with. I'd go straight away, get the bonds in. Pentuene, so I know it's going to be 1, 2, 3, 4, 5, like that. And so E isomer, so I'm looking for hydrogens across like that, and obviously my other groups. So I'm going to have that group, and I would say C2H5 down there. 1, 2, 3, 4, 5, yeah. Or you could draw this as CH2, CH3. I think C2H5 is fine. They accept both. I think they prefer this one, but I think that's fine. 1, 2, 3, 4, 5, yeah. Pentuene. Obviously, get your double bond in the correct place. That's fairly important. Next one. 7b. A chemical test can be used to distinguish between separate samples of isomer 1 and isomer 2. Straight away I know where this is going. Isomer 1, isomer 2. Thing here is it's an alkane, single bonds. This one has a double bond because it's an alkene. So although they have the same molecular formula, it doesn't matter. Reagent is going to be bromine, water. Standard test. Isomer 1 was an alkene, so goes colourless from orange, no visible change there for the alkane. Are we allowing no visible change? That's what they're allowing. No, we'll say stays orange there. We'll stick with stays orange. That's probably a safer one there. Stays orange. 3 marks. Quite a lot of marks that for, you know, a simple test, which actually it's not really any more than GCSE. Use table A on the datasheet when answering this question. Isomer 3 and isomer 4 have similar structures. State the infrared absorption range that shows that isomer 3 and isomer 4 contain the same functional group. Okay, so here's my datasheet. We're looking for this. Looking at this stuff here, not on all this, is our NMR data, which doesn't matter for the AS, and we're looking for that carbon-carbon double bond. So we're going 1620 to 1680, and so our answer is 1620, 1680. Boom, nice easy mark that. State one way the infrared spectrum of isomer 3 is different from the infrared spectrum of isomer 4. Again, I know so how they're different is going to be the fingerprint region. It's got to be the fingerprint region. So finger, just like human fingerprints, and that's the bit, remember, below 1500 is different. Always different, every molecule. In that one there, is it 3 and 4 we're looking at? Yeah. So 3 and 4, we've got very, very similar molecules, very, very similar. Obviously containing the same functional group, very, very similar layout and all the rest of it. But key thing, fingerprint region, always going to change. We're still on question 7. It's continuing. 2 alcohols are formed by the hydration of isomer 4. Draw the displayed form of the alcohol form that is oxidized readily. Right, let me try and get my head around this question. 2 alcohols are formed by the hydration isomer 4. Let's have a look at isomer 4. That's probably going to make more sense. Isomer 4, where are you? Isomer 4. 2-methyl butene. So we'll draw it down here. 1, 2, 3, 4. They're all going to be hydrogens. Oh. 1, 2, 3, 4. Right. Okay. So if we add thingy across there. Right, so the idea here is that the alcohol we could form with an OH group here and an H here, but sorry, let me add that in. H there. So we're adding our H2O in across the double bond. This, however, is a tertiary alcohol, alcohol group 1, alcohol group 2, alcohol group 3. Tertiary alcohols cannot be oxidized. It's quite a tricky question that took me a while to get my head around. If, however, we add it across the other way, so there's the hydrogen and there's the OH, this is a secondary alcohol which can be oxidized. Okay, and that's the key thing, it's saying that is oxidized. So our double bond was there, we're going to add it across there. There's my CH3, there's my H, there's my H. Oh, I just realised I've done a cheeky little error there, which I've got to make sure we don't do. Just make sure I've got that all in. Okay, now the error I've made, but I've realised, is that it's a displayed formula. So all bonds must be shown, and I believe that is correct. So there's, yeah, secondary alcohol has been formed there, which is oxidised readily, and that's the key thing. One nice little mark. Got to include all the bonds there, otherwise you are just given bond. That includes the OH bond. Very, very important. Okay, isomer 4 reacts with hydrogen bromide to give, here we go, bit of mechanisms, to give 2 structurally isomeric bromoalkanes. Name and outline a mechanism for the reaction of isomer 4 with hydrogen bromide to give 2-bromo 2-methylbutane as the major product. So bear in mind this is an electrophilic addition reaction. What we're making here is we're making CH3, CH3, okay, that's a bit wild to get my head around that. Working on slow today. CH2, CH3. Okay, yeah. So this is our normal thing there. So basically we've added the hydrogen bromide across there. Right, so it's important this because we've got obviously a middle step here. So let's draw out our molecule first. C double bond. I would probably draw it out like this because I think it just helps when you've got a bit more space. CH3, C double bond, CH, yeah, that's fine. Okay, so HBr is going to be here. Remember, this is our delta negative region, delta positive region, not required, but still we'll include it there because it's good to have. This is going to move onto there, and what's going to happen is from the double bond there, we're going to get a bond formed here. And it's very, very important that our next step is drawn correctly. Okay, so same molecule again, single bonds now, because we know that one of those bits has moved across. It's very, very important that we have the correct stuff. Now the hydrogen is going to be bonded to there to give us this portion. This is going to be where our carbocation exists there. That's very, very important. And we see the reason this is the major product is because it has 1, 2, 3 alkyl groups there. So it's the most stable. It's that tertiary carbocation, more stable. Bromine, bless him. Lone pair, got to include that, and the charge. It's going to come in, and it's going to attack just like that. So we've got 1 mark there, 2 marks, 3 marks, 4 marks, 5 for the structure, 5 marks there. Nice, easy sort of marks. But it requires us really thinking about the structure that we've got here. You get that confused the other way around, you're going to lose the marks because you're not going to produce the correct substance. You're not going to produce 2-bromo 2-methyl at all. Okay, you're going to produce 2-bromo 3-methyl. Okay, and that's obviously not what we want. That's not the correct answer. So, cracking on. Item 7 is still going. Oh, and here we go. Explain why this bromoalkane is formed as a minor product. This is what I just explained. So I would say the carbocation that is formed as an intermediate before the formation, not the best worded here, of the 2-bromo 3-methyl butane is a secondary carbocation, therefore less stable. The stability to do with what's called the positive inductive effect, each alkyl group pushing electrons on, causing a nice even spread of electrons, which gives us higher stability. So that should get you both marks there. So it's just really wording it correctly. So the idea of that intermediate product, in this case, that intermediate is more stable because it has the 3 groups. It's a tertiary carbocation. In the other one, it would be secondary, therefore it would be less stable. And that's really what I've put into words there. The carbocation is formed as intermediate. Before maybe in the formation might sound better. Yeah, is a secondary carbocation, therefore it's less stable. Boom. Oh, another mechanism. There's 21 marks this question's worth. Unbelievable. So 51 minutes in at the minute. State and outline a mechanism for the following reaction to form isomer 5. So isomer 5, where are you? Scrolling up about a mile here. Look, it's taking me forever. 2-methylbutanone. So we're starting with a haloalkane, and we are ending with an alkene. Therefore, the type of mechanism has got to be elimination. Stuff is being lost here. We are having stuff ejected. So let's start with our molecule. So we're going to have a C, Br, CH3. I'll draw this out a little bit more thoroughly this time. I'll put a CH3 there. CH2, CH3. I like to think of this one as a kind of as a cascade, if you like. Look for your halogen, go up, across, and up to that hydrogen, or it could be that one there, but I tend to go boom, boom, boom. This is your mechanism. Coming from the lone pair, that is moving onto there, that is moving onto there, and that is all of the marks. Bish bash bosh. 1, 2, 3, 4. It's like a waterfall. So find your halogen, go up to the carbon, the adjacent carbon, and the hydrogen that's attached to that. Bada, bada, bada. Obviously, bear in mind, let me just check actually that I have done this correctly. Do you know what? I haven't done this correctly, have I? Cheeky. This you got. That's good job. I did that. See, I've realised. Undo that. Now, the reason I haven't done that correctly is because I did not check where the double bond was being formed. And actually, the double bond is being formed in this position here. So it's actually the same process, bromine, but rather than going like that, I should be going up and across that way. So I'll put HO, lone pair on the oxygen, very, very important. Comes down, bonds. That's coming down onto there. Okay, and then that is coming off on to there. 1, 2, 3, 4 marks there. Hold on. 1, 2, 3, 4. Oh, there we go. Roller hydroxide ion. I was going to say I couldn't see that there. Hydroxide ion is a base in this reaction, and that's giveaway is that we've got no nucleophilic electrophilic part there, so it's acting as a base. It accepts a hydrogen, a proton. So 1 mark, 2 mark, 3 mark, 4 mark. Don't make my stupid mistake, or if you do, realise like I did where your error is. It's got to be the formation of the alkene in that first position there, and it's acting as a base. 21 marks, incredible. So question 8, I think we've got 2 questions left now. Question 8. Carboxylic acid, 3-methyl-butanoic acid is used to make esters for perfumes. The following scheme shows some of the reactions in the manufacture of this carboxylic acid. So reaction 1 from the alcohol down to the haloalkane to the nitrile and then to the butanoic acid. Fine. One of the steps in the mechanism for reaction 1 involves the replacement of the functional group by bromine. Use your knowledge of organic reaction mechanisms to complete the mechanism for this step by drawing 2 curly arrows on the following equation. So 2 curly arrows on the following equation. So let's have a look. What are we going to do? So we know that H2O is going to be produced, and that's going to be this portion here. So what we're actually going to find is this is going to move on to there, and actually think how to describe this. Well, nice to stick with that. So this is going to move like that, and this is actually going to attack that carbon there. This is going to cause the ejection of the water molecule here, perfect, and this is going to cause for the bromine to bond there, acting as a nucleophile and attacking that carbon. If we look at this drawn out, the CH2, and this is just that bit there, with the OH2 there, we could see that this would be our delta negative and this would be our delta positive region. So it is open to nucleophilic attack, this carbon is, as actually happens there. Rest of the molecule, it's not going to happen. So it's a bit more out there, but again, you'd expect this. It's later in the paper, it's the penultimate question. We're going for that much harder content now. But again, if you get your head, if you can sort of work your mechanisms, brilliant. If you can't, you're losing 2 marks. No point crying about it. Deduce the name of the mechanism in question 8A1. So, as I said, nucleophilic here because we've got a lone pair being donated and it's a substitution reaction that's occurring there. We're swapping the OH2 for the CH2 there. Okay, it's a little bit different to our normal appearance, normal nucleophilic substitution reaction, but it's still the same. So nucleophilic substitution, give the UPAC name of CH3 to CH2Br. God, let's draw this out. Don't be confused here because they're sneaky little toe rags, our old AQA. That CH3, CH2 looks like this in reality. Don't start thinking, and there's a CH, CH2, Br. So CH3, CH3, CH, CH2, Br. Perfect. So name it. 1, 2, 3 is our longest chain. So our longest chain is 3. So it's going to have prop in there somewhere. It's going to be an alkane, but what's going to be a haloalkane. So we're going to have propane at the end. What have we got here? So we've got 1 bromo, our functional group there, the bromine, the halogen. It's going to be 1 bromo, 1, 2 methyl. So 1 bromo, 2 methyl propane. 2 marks. Boom. Bromine is going to be in position 1, not in position 3, because it's a halogen. It wants to have the lowest, it wants to have the sort of highest priority, so it's going to take the lowest number. Reaction 3 is an acid catalyzed reaction in which water is used to break chemical bonds when the cyanide functional group is converted into the COOH functional group. Infrared spectroscopy can be used to distinguish between the compounds in this reaction. So, there's a lot going on in that question. So water is used to break chemical bonds. Straight away, water is used to break chemical bonds. It's a hydrolysis reaction. To deduce the name of the type of the reaction, so it's hydrolysis, identify one bond in there and a different bond in there that can be used with infrared spectroscopy to distinguish between each compound. Okay, let's have a look at here. So, I would guess we can use, here we've got the CN, so CN bond, or CN bond there. Give the range of the bonds, so we have to give the wave numbers as well. So CN there, 2220, 2260. So it's going to be 2220 to 2260. We would find an absorption. The other one, we are going to look at, it's got a few options here. I'd probably go the OH acids, I think would be my gut feeling there. My absorption range there, data sheet 2500 to 3000. And that's our marks done. That's not too bad of a question. There's a lot of words, but actually the answer isn't too bad at all. So 8C, when 3-methylbutanoic acid reacts with ethanol in the presence of an acid catalyst and equilibrium is established. Again, it's stolen my symbols. Thieves. So an ester is produced. Carboxylic acid is very expensive and ethanol is inexpensive. In the manufacture of this ester, the mole ratio of carboxylic acid to ethanol used is 1 to 10 rather than 1 to 1. Right, so okay, it's quite a clever sort of question. So we're back to equilibrium that we've already looked at once. They're coming back to it. Not seen a question like this. It's quite a nice one. So the reason for this ultimately, why is it used? Increases yield of ester. Why is that the case? So what it's going to do is, by having this massive sort of excess of this, actually the Chatelier's principle is going to say, right, well, we need to remove this, so we're going to favour the forward reaction. We're going to shift the position of equilibrium to the right in order to remove this, therefore producing more ester. So it's quite a clever use. So equilibrium position shifts right to oppose the increase of ethanol. I guess it's about the best way to say that. Right, yeah. So it shifts to the right to oppose this one, or to impose the increased moles of ethanol would also work. So it increases the yield of the ester, because the more we add of this, by doing 1 to 10, because this costs us very little, we whack loads of it in, boom, this properly shoots the right hand side here, favours this forward reaction. Okay, it really favours that forward reaction, and therefore shifting to the right produces more ester as a result. So it's quite a clever use of Le Chatelier's in the equilibrium question. But, you know, again, equilibrium has come up twice now in this paper, so do bear that in mind. Explain how catalysts increase the rate of reaction. Standard answer here. Alternate reaction. that I'll call it abbreviated because I can't bother to write it all. So alternate reaction pathway that has a lower EA or activation energy of activation. End of question 8, 12 marks. Final one here. Ethanol is an important fuel. How many have we got here? Oh, we're so close, but so far. Question 9. So this hardest part of the paper, it should be. A dilute aqueous solution of ethanol can be produced by the fermentation of an aqueous solution of glucose. It's claimed that ethanol obtained from this solution is a carbon-neutral biofuel. Write an equation for this fermentation reaction. Let's do it one by one then. So fermentation reaction, write an equation for it. So glucose, the process that occurs all sorts of places, distilleries, formation of beer, alcohol, and all the rest of it. C2H5OH 2CO2 is going to balance that up a treat. That's our equation. Tick off if you want. So we've got 5 things to do. 1, 2, 3, 4, and 5. So 2 other essential conditions for this reaction. So 2 things. So yeast is required, and so that's 1. 2 other essential conditions. Temperature. So let's go for, let's go 37 degrees. Give it a temperature. I'll give it a third as well. No O2. I'd perhaps go with actually yeast and no O2. But there's my 2 other conditions there. Name a process used to produce a much more concentrated solution of ethanol from a dilute aqueous solution. Distillation. If you've all seen bottles of vodka and all the rest, you know, distillation is the process that allows us to increase the concentration of alcohol. That's where our spirits are produced. Name a process used to produce, oh, we've already done that one, so that's that done. 4 marks in. State the meaning of the term carbon neutral. Easiest way to do this is probably no net production of CO2. The other way to describe that would be that the amount of carbon dioxide taken in when the plant grows is equal to the carbon dioxide produced when the fuel is burnt, including obviously fermentation as well. No net production of CO2 though makes that whole process a lot quicker. It's very, very much a quicker thing to write. 1, 2, 3, 4, 5 marks. Boom. 9b, a student carried out a lab experiment to determine the enthalpy change when good enthalpy, a bit more calculation. Heat produced to warm some water and a copper calorimeter. The student found the temperature of 75 grams of water increased by 5.5 degrees when 2.4 times 10 to the minus 3 moles of pure ethanol was burned in air. So, let's have a little go at calculating this then, shall we? So we know we're going to use Q equals MC delta T. So we are calculating Q, so let's put in our values. So our mass is our mass of water, so 75 grams of water. C is given to us as 4.18, and delta T is 5.5. I know it's supposed to be in Kelvin, but the thing is the difference, doesn't matter if it's in Kelvin or Celsius, the distance is always the same. If you add 273 to this, you've completely thrown your marks away, okay? Please do not do that. It's such a stupid thing to do. Answer here is going to be 1724 joules. Okay, and we're dealing in joules here and all the rest of it. So we're going to convert that now, though, into kilojoules. So therefore, 1.724 kilojoules, because the enthalpy, go back up here, the enthalpy is in kilojoules per mole, not in joules per mole. So we've converted it to kilojoules. Perfect. How many moles did we have? Well, 2.4 times 10 to the minus 3 moles of ethanol produced this energy change. So it was 1.724 per 2.4 times 10 to the minus 3. We don't want that. We want it per 1 mole. So, easy thing to do here is divide this by itself. So if I do 1.724 divided by 2.4 times 10 to the minus 3, I will get an answer of 780 18. Tell you what, let's just check that. Here's my calculator. 1.724 divided by 0.0024. Let's try that again. Yeah, there we go. 718. So we'll call it 718. That's fine. But because it's an enthalpy change, we must have it minus symbol there. We know that because it's an exothermic reaction. Energy is being released. It causes a temperature increase, and of course then some units to go with it. Deduce not finished there though. That's our 3 marks there for calculation. Deduce 2 reasons why the student's value is basically different to the value that was produced. Classic answer: heat lost to surroundings. The other one, I would probably go incomplete combustion. Not all of the ethanol, well, it didn't combust completely, therefore obviously the value there, because we know it's given this standard enthalpy of combustion, provides it's the idea of it being burned completely in oxygen. Obviously if there's a little bit less oxygen, it's going to be a different value, hence obviously as we see that. And if you've ever done this at school, it's incredibly inaccurate because of the heat loss, incomplete combustion, and all that. It's terrible, in fact. Give the meaning of the term mean bond enthalpy. So mean bond enthalpy can be used to calculate enthalpies of reactions. So we can see where this question's going now. What is the meaning of this term? So it's the enthalpy change when a covalent bond is broken, averaged over a range of compounds. I would probably go with enthalpy change when a mole of covalent bonds is broken, but I'll leave that as that. Mark scheme's happy with that. So enthalpy change when a covalent bond is broken, averaged over a range of compounds. Quote. I still like the idea of moles being in there. I'll leave it though. And finally, we're going to have to do a look, and that's the end of this question. Oh, so good. Use the data in table 3 and the equation shown to calculate the value for the bond enthalpy of the oxygen double bond in an oxygen molecule. So this is a clever one now. We've got to actually, it's not a usual one. We've got to actually work out the idea. Right, so we've got to work out what's going on here a bit differently into normal, because we're trying to work out this value. So it's quite a lot of stuff to do here. It's a bit of a nightmare really, but it's doable. It's doable. It's not a particularly quick one, but there we go. So let's write out what we've got. CH3, CH2, OH, C. Obviously we've got 2 of those. H2O. Okay, so we know that whatever's going to happen, this is going to equals minus 1,279. These values are all going to be negative because the bonds are being made. These bonds are broken. That's the way I like to think of it. Break all these bonds into single atoms, remake it all into these bits here. Positive process, negative process. So obviously these values here, that's the value to break that bond. Negative would be the value when that bond, that's how much energy is released when that bond is made. So 1, 2, 3, 4, 5 CH bonds. So 5 times 4, 12. Add 1 CC. Add 3, 4, 8. Add 4, 6, 3. That's my OH bond. Add 3 times X. Okay, that's my unknown as it stands. So we're happy with that. 3, 4, 8, 4, 6, 3, 5. So yeah, just checking I've got all those. I've got all my right values. 4, 6, 3, 3, 4, 8. Oh, forgot one. CO. Add 360. This is, we've got to remember. This is why this is tricky. You've got loads of different things put in, and then I would just say take away from that. CO, so 805 times 4 take away from that H2O, so it's going to be 6 times 463. And the magic of this should tell me that 3x, if I rearrange all that jazz, 3x should be 1488. So x therefore, which of course is the oxygen-oxygen double bond, is going to be 496. And that's the one. Remember, we're trying to calculate the bond enthalpy. We don't want to be going minus, we want to be using positives on that. And there we go. That is how that question's done. That is 1 hour 14. I'm a bit annoyed about that. 10 minutes over what I wanted. Still half hour short of the maximum time. That is the June 2014 paper. Hopefully that's been of some help. By all means, stick some comments down if you have any problems. But there you go.